then I would forget. Good morning. Friday. Here we go. Hey, just like that, we're at half the classes here. Well, that's pretty good. All right. So first things first. Well, I can't believe I managed to do this. So when I was mapping out our classes on the calendar, February 28th is a Sunday, but then there was a whole empty week that I used somehow. I don't know. But anyways, our test 2 and test 3 dates have changed. So I just want to make a note of that. The dates for test number 2 and number 3 are now test number 2 is on March, I want to say 24th. So I did update it on the Moodle page, March 24th and April 14th. So just make sure that you update, if you put it in a calendar or something, then make sure you update that. March 24th and test number 3, April, I want to say the 14th. Let me just double check. In the last week of classes there. Yeah. It still works out well, so not to worry. But we just got one review day for the final exam. I was really confused. I was kind of like, oh, why do we have an extra week here? I managed to flub it, so that's why. So here I'll even highlight this, right? March 24th and April 14th. Okay. All right, so our Webassign page is now available. I had to so if you tried to log in yesterday, it wasn't available yet because I set it to start today so that we can maximize our free trial until the 29th. So that's why I had to start it today. So our Webassign course is now available, and I'll just kind of walk you through how to set that up. Like I said, there was some issues, so I'd love it if you could kind of try it as we go along here. If you can't, then that's totally fine. And our class key, which is kind of the most important thing, is okanagan.bc and then followed by 6558 and then 9754. Kind of a weird setup, but that's how they do things. Okay. So, and what I did was on our Moodle page, I added a Webassign section. Okay. So just use a free trial for the first 2 weeks, and then you can kind of put off buying the access code until you're really sure that you're staying in the course. The sign-up instructions, because I can't actually do it on my end, I guess I could with my personal email or something, but I'm just kind of guessing at the steps. So you go to the login page, which is just webassign.net. And then you either have an account from before, right? Maybe you used it in pre-calculus or I don't know. So maybe you have Webassign from a different course. So then you might just log in and then you're gonna enroll with class key or enter class key, whatever kind of thing that hints at logging in or kind of entering a class key. And then you enter your class key, and I put a screenshot, and because it's just kind of in the middle of the page, it's so small, but when I pretend to do it, it looks like this. So it says enter a class key, and this is different from how it used to look. So If you're not coming across this, if you're coming across a page that's red instead of blue, then it should still work. I know there was a glitch, so I think the new page is blue. So you enter your class key and then you hit register, and then hopefully it registers you in our course. So let's see here. Oh, that was a screenshot. I was trying to move back. That doesn't work. So what I'm gonna do here is I'm just going to go into our Webassign just to see here, okay? So if you're able to try to log in now, that would be great, but it might be a little bit more time consuming than that, so I'm not sure. And so I put the link to our online bookstore. You can buy it in other places. I just don't want to I just want to make sure that you're not paying too much. So as long as you're paying $99.95 Canadian dollars or less, then I'm happy. Okay. I don't know where you would be able to find it for less, but anyways, if you find it, let me know. Okay, so what I want to do is open another page and say webassign.net. Okay, so when I go to webassign.net, it looks like this. And up in the top right-hand corner, you've got enter class key. And so it used to be that you just click enter class key, and then it would prompt you to log in or create an account, and then you can enter the class key. Of course, they will be pushing you to purchase the access, but you can probably just say skip this or not now or something like that. So they want their cash money, but not yet. No, no, no. So once I log in, because of course I have control of the course, hey, there's 2 of you managed already. That's awesome. That's great. So seems to be working. If you're having trouble, then let me know, but seems to be okay. So my view is not very nice. I'm going to go to the student view and kind of show you around here. Okay. So I kind of got ambitious and I posted, I guess, 4 assignments. Okay. The first one is just getting started with Webassign. It's just how do you enter answers and that kind of thing. So just so it's easier to fill in answers properly later on. Posted homework for 1.1, 1.2, and 1.3. I might pull the 1.3 homework if we don't get to it this week. So in general, all our homework will be due at midnight on Fridays. So I'm sure you have better things to do on your Friday nights. But if not, then you could be doing math homework. Of course, you can do it beforehand. So all our homework is going to be due on Fridays at midnight or 11:59 p.m. just so it's not confusing. And I made all of these due on Friday, the 22nd, so next Friday. And it's showing up weird because of the 1 hour time change, but on your end it should show up fine. So you've got your assignments here. Sorry, I don't have a pointer on a web page, so I'll just kind of explain where I'm pointing to. For the My Class Insights, that's where you'll be able to find kind of extra practice problems. It'll highlight, the problems you got wrong or had to kind of try again. And then it'll be able to kind of tutor you in a way to help you with those topics that you kind of had a hard time with, right? So it'll pick up what was difficult for you, and maybe take you to that section in the textbook, which I know, well, it won't, but maybe some more problems or something like that. Right? And then this is on the iPad. It's got the same layout on the desktop, but I know when I go on my phone, it's just all mumbo jumbo, but somewhere on the page that you're on, you've got about this class, and I can't seem to change the time to be proper. I don't know why it's misbehaving. You know what time class is, so that's fine. But that's where the ebook is, right? So the calculus, the 9th edition, early transcendentals, that's your ebook. So if you go here, if you want to read further, and a lot of questions will just kind of, hey, do you want to read more about this problem? And then it'll just take you to that section in the textbook. So, so you don't really necessarily need to read the textbook, but you can. So here, I don't know, I guess I don't really want to open it on my iPad. It's going to take forever, but this is where you access the ebook, right? And so that'll be there, blah, blah, blah. Oh yeah, here. So chapter 1, like I said, it's going to take a while, but you can do cool things like take notes and kind of make little index cards and highlight and, I don't know, just cute things. So, all right. So there's your Webassign. Close student view, great. Okay. So make sure that you are able to sign in and get into the course. And like I said, depending on how far we get this week, I might bump the assignments a little bit, at least for 1.3. I don't think we'll get there today, but that's okay. All right. I have the chat open. It's crickets out there today. That's okay. Friday morning. If you do have a question, let me know. Otherwise, we'll get started on a little bit of review. We didn't really do a ton last day, but we did end off with talking about domain.
Just to quickly point out, if you try for the Webassign stuff, you might, if you already have an account, once you get registered, or if you're logged in and have entered the class key, it will boot you back to the initial My Account screen, and it won't initially show the class. You have to log out and log back in before it will update and show you the classes right there. Because I was very close to freaking out.
Good to know. Thank you for pointing that out. So just to summarize, I'll put it in our notes here because that's really important. So if you have an account, you can register and then log out and then log back in. Is that the gist? Okay. So I will put that if you have a Webassign account already, and it might be just a good kind of trial and error thing. If you have a Webassign account, I guess log out is 2 words. Log out after you have registered. Then log back in. Cool. That is really good to know. Thank you, David. All right. Good. Webassign, a little bit prickly in the beginning, but for the questions that they have. It's pretty good. All right, so just as a quick review, right, just kind of flipping back here. We just developed some function terminology, right? So we talked about function terminology. And I'll just kind of leave it at that because it was just on Tuesday. But also we talked about domain rules. Right. The first one being, and just kind of shorthand, because you've got them in your notes, but because we're about to use them, I just want to highlight them again. So the domain rules, first thing, we cannot divide by 0, right? So any input that makes us divide by 0 has to be extracted from the domain. So we can't divide by 0. We can't take the even root of a negative number, right? So usually we just say the square root, but we actually mean the square root, the fourth root, the sixth root. So any even root. We can't take the even root. Oops. The even root of a negative. Right? So whatever x makes us take an even root of a negative, we have to extract from the domain. And third, which we'll kind of parking lot until we introduce logs again, but we can't take the log of anything but a positive number. So we can't take the log of 0 or a negative. So we can't take the log. And here, because we did, I can't remember who asked the question, but it is a really good thing to clarify, of any base. So we can't take the log of any base of 0 nor a negative, right? So we have to take the log of a positive number. All right, so we go back to our notes here, and you'll see that I posted notes for sections 1.2 and 1.3, just kind of shorthand summaries of everything that we're going to walk through. And because we're just doing review, it's really just kind of a reference document. So we're not going to do a ton of problems in there, but it's just stuff we need to talk about before we can keep going. So it is going to feel tedious, but we have to do it. Just to make sure we're all on the same page. All right, so here, we'll finish our review there because it was just so brief. And we'll start with an example. In fact, I'll put it on a new page. So if we have to find the domain of each function, we're going to go on and on and on about the domains. And so we need to kind of get comfortable again working with domains. And you've solved problems like these in 12 or in pre-calc. So here, if you've got a square root, right away you need to think, okay, I can't take the square root of a negative, right? And here you've got a fraction, so you need to make sure that, okay, all x's are allowed except the x's where I'm going to end up dividing by 0, right? Because that has to be extracted. So here, can't take the square root of a negative. And here, we can't divide by 0. So for A, how do we kind of summarize that? Well, so to find the domain, I need to make sure that x plus 2 is greater than or equal to 0. I can take the square root of 0, it's just 0, right? But if we had to exclude 0, then we would not include the equal to 0, right? It would just be greater than 0. So in this case, right, working with inequalities, here, the only thing I need to keep an eye out for with inequalities is if I multiply or divide by a negative, then I have to switch the sign, right? So as soon as you see an inequality, you have to kind of hold up, okay, I can use it as an equal sign, except when I'm dealing with multiplying or dividing negatives. So here, if I just treat this as an equal sign, I would subtract 2 from both sides to solve for x. And so subtracting is fine. So x has to be greater than or equal to -2. Okay. So let's see here for the next one, or actually, let's summarize the domain, and I'm going to use interval notation. A lot of the time, Webassign requires answers in interval notation, especially for the domain. So that's what we'll kind of get in the habit of doing. It's also the easiest way, I think, to report on intervals. But so here we go. So if x has to be greater than or equal to -2, and just to make sure that what you're doing kind of makes sense, we'll plug in -2. -2 plus 2 is 0. Okay, so that's fine. It's allowed to be equal to 0. Greater than or equal to -2. Let's do x equals 1, right? 1 plus 2 is in fact greater than or equal to 0, right? So you can always just kind of check your way back and make sure that what you're saying makes sense. So starting at -2, right, including -2, and then we're allowed to go up to positive infinity. And I can't remember if I mentioned it in this class or if it was another class. I get better as the term goes on to kind of keep my classes separate in my mind, but for now, I can't remember if I mentioned it, but infinity is not actually a number. So you have to have round brackets around infinity always. And that goes for negative infinity as well. So because we can't actually ever get to infinity, it's just kind of an idea. So this would be our interval notation for the domain of A. Let's do B. So we've got g of x is 1 over x squared minus x. And so what I need to do is I need to avoid dividing by 0. So just first thing I want to do is just say, okay, well, x squared minus x can't be equal to 0, right? So what I'm going to do, because I've got an x, I've got a common x that I can factor out. Because I want to simplify this a little bit, just to make sure I'm catching all the options here, I've got x times x minus 1 can't be equal to 0. Okay. So there are 2 values of x that give me a result of 0. Right? So here, if I let x be 0, 0 times anything, 0 times -1 in this case, would be 0, and 1 minus 1 makes 0 times 1, which is 0. So the 2 values to avoid, right? This says x cannot be 0, and this says x cannot be 1. Okay. Kind of 2 different approaches that I use here. Right here, I'm doing, I'm telling it which ones I want to target, and here I'm trying to figure out which ones I don't want to target, and that's just going to be a matter of practice, right? So to see which one's easiest. But if you're trying to avoid being equal to 0, then usually it's just easier to set it up this way. Okay, so in interval notation, right, I'm allowed to have the set of real numbers as my x's except 0 and 1, right? So I'm going to go from -infinity to 0, but not including 0. And then I'm going to pick up again at 0, but not including 0, and go to 1, and then, but not including 1, and then pick up again and go from 1 to infinity, right? So you want to get those breakpoints in. So our domain then, in interval notation, would be -infinity to 0. And then we link them with that u, so the union, right? 0 to 1, union, 1 to infinity. Oops. Oh, can't seem to manage. There, I'll take it. Drawing infinity. It's usually kind of lopsided for me. Okay, so here we link intervals using the union, which is just a capital U here. And that's from set theory. Okay. Great. So we'll come back and we'll deal with more domains, but that's kind of the gist of it to start. Yeah. And the main things to look out for. All right. So let's see here. We go back to our notes. Where were we? To be able to figure out whether a function is or whether an expression is a function or an equation is a function, we need some tools, and the easiest tool is the vertical line test if you have a graph. And so the key thing with a function is that each input can only yield one output, right? And so the vertical line test is kind of a graphical check to see if you have a function. There are graphs that are not functions, right? So here we've got a kind of a prime example, and there are kind of common expressions that are not functions, but that's okay. Things maybe don't have to be a function, but for us, right, here in the beginning, right, we need to have functions. So to check it, we use the vertical line test, and the vertical line test just says you should be able to draw a vertical line. So a vertical is like this, and then horizontal is like this because you've got the horizon right there, like this, right? Another one of my, you only need to remember one of them to remember the other. Right, so you need to be able to draw a vertical line at any point on the graph, and it should only intersect the graph once, right? And that's just a graphical check of, does each input X, right, only yield one output Y? Okay, so I'm just going to grab that whole kit and caboodle and say, in order for, oh, and you know what? Yep. I should try to indicate that that's the end of our example. So in order for an expression or equation, just as a side note, an expression doesn't have an equal sign, and an equation has an equal sign because it's equation. Often just equations are what we're dealing with. In order for an equation, and you know what? So common, in fact, I'll just simplify this a little bit. In order for an equation to be a function, each input, so each x, can only yield one output, y. Okay. So we can check it using the vertical line test. Right. But sometimes, you might be asked to, you might be given an equation, and if you're able to find that, okay, well, y equals plus minus is the typical situation, plus minus whatever, then you get two outputs for each input, and so then it would not be a function. Anyways, I only mention that because it comes up on the 1.1 assignment, right? So at first, I like to just have only questions that we've covered in class, but then I was like, no, you know what? I'm gonna let you guys think about it. We are in calculus after all, so I won't spoon feed you as much as I would like to. Try not to. Okay, so vertical line test, just to see if you have a function, that means that you have to have a graph. You can definitely take an expression or an equation and just graph it in Desmos and then do the vertical line test, right? So I'll say, given an equation, you can graph it in Desmos and then use the vertical line test. Call it VLT. Sorry. Thank you. Sorry, someone's selling chocolates. And it's actually really convenient because she usually comes by like just before the weekend. And so, but not today. All right, so even if you don't have the graph, you can make the graph in Desmos, right? And so use your resources. All right. We're going to deal with piecewise defined functions. So what that means, and you've seen piecewise defined functions before, is the function behaves differently for different regions of the domain, right? And so, and that's okay, but we need to talk about, what they are officially. So functions, I've got a page break, so I'm going to use that, even though it looks weird here. Functions that are defined by different formulas in different parts of their domains are called piecewise defined functions. So we'll just throw that in here. Functions that are defined by different formulas in different parts of their domains are called piecewise defined functions. So we'll do an example here. So a piecewise defined function is usually wrapped up in one large curly bracket. And then here we specify the parts of the domain where it applies, right? And it can be that you have holes in your domain, right? There might be stretches of the domain where it's not defined, where the function's not defined. So don't be thrown off if that happens. But so we're going to use this function, right? So if x is less than or equal to -1, then the function is a straight line. And so we're going to start seeing little functions like this and try to classify them. And we'll do more of that in the next section, but try to classify them by what type of function it is, right? Because that'll help us kind of visualize what this thing's going to look like. 1 minus x, that's a linear function, right? Y equals mx plus b. There's just one x and its power is 1. So then we have a linear function. Here we've got this parabola, right? This square. So I know it's going to have this kind of parabolic shape, okay? But only for x greater than -1. Okay? And so we're going to evaluate it at 3 points, -2, -1, and 0. And then we're going to sketch the graph from there. So we've got f of -2. Well, -2 is less than or equal to -1. And so here we've got 1 minus x. And x in this case is -2, so I'm going to throw that in. 1 minus -2. Dealing with negatives, right? Minus a negative is a plus, so 1 plus 2, which is 3. Showing way more work than you have to. Maybe I'll try to keep it all on. I'll do them side by side, just so we don't have to scroll around so much. F of -1. So first thing I have to do is take this x and figure out what part of the domain am I in. Am I in x is less than or equal to -1? Yes, I am, right? Or x greater than -1? No, I'm not, right? So I'm still at 1 minus x. So 1 minus x, which is 1 minus -1, 1 plus 1, which is 2, right? I'm just showing you exactly what's going on there. But even if you just skipped from here to 2, so 1 minus -1 is 2, that's totally fine. F of 0, now x is greater than -1. And so what I have, my function now is x squared. So I've got, I'll jot that down, which is 0 squared, which is just 0. Okay. I don't have a lot of points. So these 2 points, -2 and -1, we're on the straight line, right? So we'll be able to draw that straight line. For the parabola, it is just x squared, so we should be pretty good at drawing x squared. But you might need to find a couple more points to plot, just if you have to actually graph this thing. So, but for us, I'm just going to put it here. So x and y, here's my graph. First things first, I've got -1, -2. Not very good spacing, is it? 1, 2, 3, 4, 5. Let's see. Okay. I'll clean this up here. Move it a little bit closer. Okay. So the straight line, it goes from x less than or equal to -1. And we know what it is at -1. And so we know it's at 2. So here I'm at, oops. 1, 2, 3, 4, 5. So when x is -1, the function is at 2, so an output of 2. And I'm going to use a closed dot because it's including that point. And then my next point on the line is kind of here at -2, 3. I'm going to use this to draw my straight line. And it's just going to go through that point, right? To draw a straight line, you only need 2 points, and then you can use a straight edge to connect them. For the parabola, I know when x is 0, y is 0, so maybe I'll use a different color here. So I know I've got that point there at 0, 0, right? What I'm going to do, because it goes up to -1 but not including -1, one thing that I will do is I want to figure out what the behavior is at -1, right? And so I'm going to go -1 squared is 1, so it's going to go up to -1, 1, right? But not including 1 or -1, right? So like this, and then just knowing the shape of a parabola, I'm just going to kind of go like that. Okay, so we've got this jump at -1 where, okay, so if you're coming in from the right, then you're coming in on a parabola, and then we've got this jump to a straight line, or from the left, either way. Okay. That's the end of that. The absolute value function is probably a function you've worked with before. In short, it just takes any value, positive or negative, and just returns the positive of it, right? So if it's negative, then it essentially drops the negative. There's a little bit more that we'll talk about, but essentially drops the negative, right? So the absolute value function, is a piecewise defined function. And I've got that little summary here that we'll grab. Okay. So the absolute value of A, remember the absolute value function, you're just going to denote it by 2 vertical lines, making sure that they don't look like ones or something weird, right? You just, sometimes I extend it off the line a little bit just to highlight that it's vertical lines, right? Often the context will make it obvious that it's an absolute value function, but just be careful. So the absolute value of A is just A if A is positive. So if A is greater than or equal to 0, then it's just going to return A, right? So here, if A is positive, here, it's going to give you negative A. Okay, so the absolute value of A is negative A if A is less than 0. Okay, so that looks weird, right? But if A is less than 0, so -3, for example, then -3 is positive 3, right? So that's what's actually going on with absolute value function. So if A is negative, right? Consider A is -3 just to have it, then the absolute value of -3 is -3, which is 3, right? Therefore, returns the positive, right? Kind of in quotes, kind of drops the negative. So let's do an example with the absolute value function, just working with the absolute value function And you probably know already what the graph of the absolute value function looks like, right? It's just this V, right? Where it's a straight line of y equals negative x and then y equals x. But let's see. So the absolute value function f of x is the absolute value of x is really saying that, and just kind of combining f of x equals the absolute value of x and what we just defined up here right now in terms of x instead of a, that's okay. It doesn't matter, right? It's going to be x if x is greater than or equal to 0, and it's going to be negative x if x is less than 0. Okay. So really here you've got, remember you can swap out f of x and y, right? Y equals x is a straight line, right? Just kind of cross the diagonal. So we can draw that first. Y equals x. And I've got my x-axis, my y-axis. Okay. If x is greater than or equal to 0. Okay. And then if I draw a negative slope, right, a slope of -1, then and the intercept of 0, then I have this kind of y equals negative x if x is less than 0. Right? So we make this V graph. Okay. Good. We'll talk more about different functions and just being able to recognize functions when we see them, right? So we should be pretty good at recognizing linear functions, kind of parabolic functions, and we'll talk about a few more in the next section. But until we do that, we'll talk about some symmetry. A function can be either even or odd, right? And so I guess this is the end of that example. A function can be even or odd or neither, right? I'll show you kind of most common that it's neither even nor odd, because even and odd have these very specific criteria, right? And so if you're able to take f of negative x, okay, and you can kind of rework it and massage it and return just f of x, then f of x is going to be even. Okay? What that means is the output for negative x is the same as for a positive x. That's only true if you're symmetric about the origin, or about the y-axis, sorry, at the origin. So if f of negative x equals f of x is even, meaning it is symmetric about the y-axis. Okay. And you can think about that, right? So if I'm able to plug in a negative x and just kind of rework it and I get the same output as if x was positive, then you've got this kind of symmetry So x squared is even, right? Because it's symmetric about the y-axis. Whereas, oops, if you take f of negative x and it gives you negative f of x, okay? So if you're able to rework the equation and extract a negative outside just the function, then f of x is odd. And this one's a little bit harder to wrap your head around, but it's symmetric about the origin, and it looks weird. And in fact, I'm going to bring in those graphs that I have in the handout. So an even function we talked about looks like this. Yep. I'll scoot the other one down. There. So the odd function looks like this. Okay. F of x is odd, meaning it is symmetric about the origin. And for me, I always kind of have a hard time thinking about that. So symmetric about the y-axis, fine, on board, right? But here, if you have an odd function, then it just kind of looks like this. And then it just kind of swings around at the origin and kind of symmetric that way. Kind of hard to visualize, at least for me, but that's okay. So if you see this kind of shape, x to the power of 3, for example, it's odd, then you've got an odd function. Right? Usually we just end up using, notice that the trick that we've used here is f of negative x and f of negative x, and it just lands us in different positions, right? Either at f of x or negative f of x, or more commonly neither, because these are very specific criteria, right? Like we said. So in order to determine if a function is even or odd, you can evaluate it at f of negative x to see what happens. Okay, so let's write that down. In order to determine whether a function is even or odd, we evaluate f of negative x and simplify to find f of x, then it's even. Negative f of x is odd, or neither. Well, then it's neither. Kind of goes without saying. Okay. So let's do a couple of examples. So what we'll find in this course is there are just kind of algebraic things like this that you can use to prove definitions. And so that's a little bit different from how we've been doing math in the past, I feel, just because you kind of have to get used to saying, okay, well, I've got the definition, so here, usually I would just give you the definition of even and odd, and then I wouldn't necessarily highlight this for you. Of course, it's the beginning of the course, so so this is what I'm doing. But here, right? Determine whether each of these is even or odd, you would kind of have to land on that on your own, right? Okay, well, I'm taking f of negative x in each case, and then seeing if I can manipulate things, right? So just kind of slowly releasing you to fly on your own, slowly. So, so what we're going to do, we've got 3 functions, and we're going to determine if they're even, odd, or neither. Okay. So f of x, I'm just going to write it out here, x to the 5 plus x. Okay. So what I'm going to do is I'm going to take f of negative x. So now I'm just going to plug in place of x, right? I'm going to plug in negative x as one thing. So negative x to the power of 5 plus negative x. Okay. Even powers, we drop the negative, right? Odd powers retain the negative, right? So we get negative x to the 5 minus x. I can manipulate this, right? I can extract a common negative. And so what I can do is I can write negative x to the 5 plus x, right? And then just notice that this is f of x. All right, so what I've landed on here is negative f of x. So what I can conclude then is that this is an odd function. So this is equal to negative f of x. Therefore, f of x is an odd function. So what I want you to do is just take a little bit of time. I'll give you, 2 or 3 minutes to work through B and see where you get to, and then we'll do them together. So I'll just pause here. So let's keep going. G of x is 1 minus x to the 4th. Now, one thing that you can kind of start to do, and just as a quick check, and it'll come up in the next section, is here, our highest power is odd, right? So if anything, it's going to be an odd function, right? Here, my highest power of x is 4, which is even. So if anything, it's going to be even, right? And so that's just kind of a quick check-in point. Same thing here, x squared, the highest power is 2. So if anything, it would be even. Right? So b, g of x, is 1 minus x to the 4th. So what I'm going to do is I'm going to take g of negative x and see what comes out. G of negative x is 1 minus negative x to the 4th. Negative x to the 4th, because I'm taking an even power, it's just going to drop the negative, right? And so what I have is I have 1 minus x to the 4th, which is just back at g of x, right? And so here, by definition, this is an even function, which equals g of x. Therefore, g of x is an even function. Of course, kind of, if you know the games that they play, the third one is probably going to be neither, right? But let's just have a look. So C was h of x is 2x minus x squared. So h of x is 2x minus x squared. So what I'm going to do again, h of negative x, okay, just substitute negative x in for x. So we've got 2 times negative x minus negative x squared. Okay. I can pull this negative outside, right? Negative 2x, and then minus x squared, because the negative x squared is just x squared. And so you get negative 2x minus x squared. I can't rework this into any version of 2x minus x squared, right? Not negative 2x minus x squared, well, in brackets, right? So, which is not equal to h of x nor negative h of x. Therefore, h of x is neither even nor odd. So pretty fun. Once you kind of get the hang of it, oh, I just use negative x, and then I just kind of manipulate it a little bit, then, I don't know, I like seeing if things are even or odd. Soothing. Okay, so the last thing that we're gonna kind of review in this section is increasing and decreasing functions, and we'll just kind of bring in the definition and have a look at an example. But for now, we're just dealing with increasing and decreasing with a graph. So it's kind of easy to see when things are increasing and when things are decreasing. I'll put it on a fresh page here. Okay. So by definition, right? And so eventually what we'll do is we'll start using this definition, right? If I'm able to pick an x1, so one value of x, where the output of f of x2 is greater than the f of x1, then we have an increasing function, right? Looking at this is hard to wrap your head around, but if you have, and I tweaked this a little bit so you don't have this graph, but you can copy it out now. Oops. Right. So just as an example, right, here, if you've got different cutoff points, x1 and x2, right, then the output at x1, if it's less than, right, so if it's less than the output at x2, meaning that you're slowly increasing as you move from x1 to x2, so as you move from x1 to x2, you're increasing, well, then you've got an increasing function. But in general here, this graph is going to be increasing from A to B, and then it's decreasing from B to C, right? And then it's increasing again from C to D, right? So you can check it with the outputs, or if you just kind of want to have a look here, right? It's increasing on A to B, on A to B. I'm not going to include B, and this is going to come up more in this course, right? But at the peak, at this maximum, there's no slope, right? So there's nothing kind of happening here. We're kind of balancing on top. So I'm not going to include B as the increasing. You could, it's not, life or death, but and let's use green here. So from B to C, we're decreasing. Decreasing, and same thing with the minimum, right? So on B to C, and then of course we're increasing again. On C to D. Okay. And I might include that endpoint because that's where it ends, but kind of jury's out. You can use, maybe I'll use round brackets all around, just so it's less confusing. There. Okay. So that's kind of increasing and decreasing. So given a graph, you should be able to identify the regions where it's increasing and decreasing. And then we'll talk more about it later in the course. All right. So 1.1, heavy hitter, okay. 1.2 is just a review of all these essential functions that we're going to be able to or need to recognize and need to kind of know what they look like. So the 1.2 notes are really bland and really boring. I managed to squeeze it onto 2 pages. So if you wanted to kind of have it handy somewhere just to refer to throughout the course, then that might be useful. Linear models, we've already talked about linear models, right? Y equals mx plus b. So here we go. Check this out. How cheater is this? So for this section, we're just going to talk about stuff. This is review. So there's nothing really to do. There's a couple of problems that you've got. Uh-oh, now I've done it. Can I squeeze this onto 1 page so that I don't have it spanning a ton of pages? I don't know. I'll see if I can do it before I post the notes. So section 1.2 is on essential functions. Okay. So here we'll review the functions that we need to be able to recognize and know some properties of, right, such as the domain. So here we review the properties of the most common / essential functions. Okay. So the first one we've already kind of talked about. Linear models are just of the form, typically we use mx plus b. You can use ax plus b or b0 plus b1x is more for stats, but it doesn't matter as long as you have one x where the highest power of x is 1, right? And then you can allow for some y-intercept. If it's 0, it's just, it goes away. One thing that's kind of more useful is the point slope form of a line. So if you have, because here, right, this requires that we know the slope and the y-intercept, right? The y-intercept is a point, it's where x is 0, right? And so the slope intercept form of a line which is y equals mx plus b requires that we know the slope as well as the y-intercept, requires that we know the slope and the y-intercept, right? Which is going to be at, maybe I'll do, the y-intercept is the point 0b, right, where x is 0. Okay. If we're solving problems, right, that might not be the case. We might just know a point on the line, right? So kind of a more general version of a line. In general, we can find the equation of a line given only the slope and any point on the line. Not just the y-intercept. Right? The y-intercept is a special case, right? And so here, oops, copy. Maybe I'll make it a little bit bigger. So the point slope form of the line. So an equation of the line that passes through the point x1, y1, allowing for any point and has a slope of m. So we still need to know the slope is y, which is just that y equals mx plus b. So we have to have a y and we have to have an x, right? And so y minus y1 is the slope times x minus x1, where x1 and y1 come from that point that we're given. Now, if we use the point as 0b, right, the y-intercept, then we'll arrive at y equals mx plus b. Notice if we let x1, y1 be 0b, right, the y-intercept, we find that y minus b, right, y1 would be b in this case, is equal to m times x minus 0, right, which is our x, x1. And then if I rearrange this, right, m times x minus 0 is just mx, and then I can add this b over here. So what I land on is y equals mx plus b, right? So therefore, arriving back at the slope intercept form of the line. Okay. So straight lines, of course, we're going to use them a lot. And so it's good to kind of be comfortable with manipulating straight line functions. We're also going to deal with polynomials. So polynomials, of course, I'm just going to copy this in here so we have it. Polynomials are things that look like this. So if you have multiple powers of x and they're all strung together with addition and subtraction, then you have a polynomial, right? So it helps to be able to recognize polynomial. And so here, this is a polynomial, right? Kind of nasty, but you've got different powers of x with coefficients on each of the x, right? And the domain for any polynomial is the set of real numbers, right? Which is from negative infinity to positive infinity. We're also going to talk about the degree of the polynomial. So the degree of the polynomial is the highest power of x, right? So here, the degree of the polynomial is the highest power of x. Okay. And the degree of the polynomial, we use it to to get an idea of the behavior of this polynomial, the overall behavior of a polynomial. So we use the degree, and like I said earlier, right, if you have the highest power of x is even, then you have an even function, right? And if it's odd, then you might have an odd function, if anything, right? So we use the degree of a polynomial to, I'll say determine, but it's not really sure. To determine the overall end behavior. So we don't necessarily know what's going on. So if we have something nasty like this, we don't know what's going on in the middle, right? But we will know what's going on with the end behavior, knowing that this is a degree 6 polynomial, right? So knowing that this is an even polynomial, we know the end behavior. So random things can happen in the middle, but in the end, what we'll see is that we'll have this kind of parabolic shape similar to x squared, right? So the end behavior can be determined from the degree of the polynomial. So the end behavior. So we use the degree of a polynomial to determine the overall end behavior. So if you have an even degree, there are kind of two situations. I'll draw my X, Y grid here. Okay. And so if, and maybe I'll use a lighter color green here. So first option is that we've got these kind of arms going up like an x squared, right? So if you imagine x squared, it might look something like this. And I'm doing dots in here because, like I said, we're only talking about the end behavior, right? So things can bounce around in here, right? But as the x's increase and go towards negative infinity and positive infinity, we're going to be able to determine the end behavior. So this is if a subscript n is greater than 0. Now, just referring back to our general polynomial here, a subscript n is the coefficient on our leading term, is what it's called, this highest power of x, right? So really what it's saying is if you've got a negative polynomial, then it's going to be flipped kind of down on the x-axis, right? So if you've got a positive coefficient, then you've got these upward facing arms, and if it's negative, then you've got these downward facing arms. And this is if a of n is less than 0. For an odd degree, if we think about x to the power of 3, for example, right, that would be an odd degree. X to the power of 3, and I don't know if you can see me, it's so zoomed in, I don't know how to figure out how to zoom it up, but anyways, x to the power of 3 kind of looks like this, right? So and then if you've got a negative constant in front or coefficient, then it's going the other way, right? And so same idea, depending on the degree and the coefficient, you'll be able to figure out the end behavior. So let's see here. X, Y, and if a subscript n is greater than 0, anything can happen in the middle there, I guess I kind of scooted it out a bit, but that's okay. And then if the coefficient is negative, then it switches and it's going up on the negative x's and kind of down on the positive x's if a subscript n is less than 0. Right? So it just depends. Okay. So looking at this nasty polynomial here, right? 2x to the 6 minus x to the 4 plus 2 over 5x to the 3 plus the root of 2. You can graph it in Desmos. But already we know that because this is a positive coefficient, right, on the highest power of x, I know I'm going to be facing up. And because x to the power of 6, so my degree is 6, I've got an even degree, then my overall behavior is going to be something like this, right? Kind of arms facing up that way. And then anything can happen in the middle here. Right? And kind of important to remember that the domain of any polynomial is going to be the set of real numbers. You can put in any value of x and it'll give you an output. Okay. So let's see here. Next one is, we talked about polynomials, power functions. Power functions in general are if you have, oops. I should have brought this in as a PDF. X to the power of a, so x is in the base, and then the power is changing, right? So here we've got a polynomial, we've already seen a power function, right? So let's see if I can I bring all this in? We'll see. I can. Now I've overcommitted. Okay, well, knowing that I can do that, let me just start over. Bring this in so we just have it all compiled here. Oh, sorry. Man, so crazy annoying. There. Sorry, I lost you guys for a second there. I'm back. I'm sure nothing changed on your end. Okay. So if you have x to the power of a, right, notice that x is in the base. Right, so x is in the base, and that's a power function. Okay, and so you can have different values of a, which is the power. So if a is a positive integer, then we've got essentially a polynomial, right? And so we already discussed how that's going to behave. So let's talk about the other two options. Right? If the power is 1 over n, where n is a positive integer again, remember that's how we use roots, right? The nth root, we raise x to the power of 1 over n. So, I guess I didn't bring this in earlier. You know what? I'm gonna condense our notes a little bit. I'm going to cut this there. It's in your notes. So this is a polynomial. Right? It can get fancier, but essentially it's a polynomial, right? Now I've committed to their fancy breakdowns here. This is how we find the nth root, right? If you need the 14th root of x, right? Kind of putting the 14 inside that hook, right? So the 14th root of x, how you do it on your calculator is you take x to the power of 1 over 14. So this is the same as x to the power of 1 over 14. Okay. And the behavior of the roots, it all depends on if it's even or odd, just like for the polynomials. So the behavior of roots depends on whether the root is even or odd. Okay. So if it's even, then you get this kind of behavior, right? So you've got x and your y, then you get that kind of behavior, right? The root of x, and it changes a little bit depending on how high the power is, right? Or how large the root is, I should say. But if it's odd, oops, IFF, that's if and only if. If odd, which I guess might work here, but it's not what I meant to do. Then you get kind of the x to the power of 3 situation, but on the x-axis. I don't know, I just kind of did that weird, but right, then the general shape kind of looks like this. Here, we've already talked about, okay, I can't take the even root of a negative number, and that's because it doesn't exist. Oh man. Sorry. When I get a phone call, it moves everything on my screen. Sorry. That's what we're seeing here, right? We can't take the even root of a negative number because it doesn't exist there. Right here, we can take the odd root of a negative number because it exists. Right? Finally, we've got the reciprocal function. Kind of keeping with the, the reciprocal function, right? If you have f of x is x to the -2, what's that actually saying? Well, this is the same as 1 over x squared, right? And so if you've got a negative power, it just means that you should be bumping it down to the denominator of a fraction. And how these graphs behave in general, right, is if you've got the graph of 1 over x, and let's try the 1 over x squared. So I'm going to go into Desmos to see what it looks like. So 1 divided by x should look kind of familiar, right? What if I try 1 divided by x squared? And I want to make sure that my squared stays on the x down here, so just be careful. It did. Okay, so in general, we're going to have these asymptotes, and it just depends on if you've got even or odd powers of x again, right? And so, but once you know the general behavior, right? Let's try 1 over x to the power of 3, right, behaves similar to 1 over x, right? So these odd powers, if they're in the denominator, have this kind of I don't know, 2C shapes, right? Whereas if you have even powers, then they go up together. So let's say, so the odd powers of x kind of in general have this shape, and I'll use a different color. Okay. Whereas the even powers, if it's in the denominator, right? The even powers of x go up towards infinity together. And it might move closer or further away from the origin depending on the power, but just knowing the general shape that you're expecting to see here is going to be really useful. So then we move on to rational functions. So rational functions is just a fraction of a polynomial over a polynomial. And these can be kind of as simple as 1 over x, right? Or as kind of nasty as 2x to the 4 minus x squared plus 1 over x squared minus 4, right? Which would end up looking something like this. And we'll get there, but right, and so we've got 2 asymptotes because x can't be -2 or +2. So rational functions, yeah, let's bring it all in. Why not? For completeness sake, I'm not drawing that, right? But I will highlight that once you've figured out the domain, and we'll do more domain problems later, but or throughout the course, x squared minus 4, if you factor that out, right, then you're going to find that x can't be +2 and x can't be -2. And so that's why we've written the domain like this. But really what it's saying is that we're going to have asymptotes or vertical asymptotes at plus and minus 2. Has vertical asymptotes at x is plus minus 2, right? Which is what we're seeing here and here. Okay. To summarize all these, and I only included algebraic functions, they're not really a standalone thing, right? All of these things that we've talked about are algebraic functions. If we can combine them with addition, subtraction, multiplication, division, powers, roots, whatever, then we just call them algebraic functions. So algebraic functions are just distinguishing between algebraic functions and trigonometric functions. Right, so all the functions that we've talked about so far are algebraic functions. Right. So I guess I can bring that in. So all the functions we have discussed so far are algebraic functions. So I don't want you to kind of be thrown off. As soon as we say algebraic, all we're really saying is algebraic just means addition, subtraction, multiplication, right? All those kind of, etc. All those fun things that we can do, right? That's algebra. And so we call them algebraic functions. And I only bring that up because it can be kind of a little bit confusing, right? Got this terrifying sounding word, but it doesn't mean anything really. All right. Something as simple as this, the square root of x squared plus 1 is an algebraic function, and something like this, nasty, right? We're not going to do anything with those. Trig functions. Now, we're going to do more trig than we did in pre-calculus, that's for sure. And I don't know, especially if you took pre-calc last term, you might not have gotten very far into trig because it was a weird term. So I'm just going to introduce trig functions kind of slowly. But for now, let's just kind of recognize the sine, the cosine, and the tangent of x and their graphs. So for example, the sine starts at 0, 0, right? Or goes through 0, 0, the origin. And then the cosine starts at 0, 1, right? And so how I remember these is you just kind of come down to the y-axis and then alphabetically, cosine comes first at 1, and then sine goes through the origin, right? So you want to remember which one starts at 0, 0 and which one starts at 0, 1. And then both sine and cosine have a period of 2 pi, meaning that you can start here at 0, 0, and then you go a distance of 2 pi, and then it cycles over again. Same thing with the cosine, right? Here we start at 0, 1, and then I go down, and then I go up, and then once I've gone a distance of 2 pi, then it starts over again. So it's cyclical, right? And so the time it takes me to take one revolution is 2 pi, right? Whereas tan of x has all these nasty asymptotes, and it only has a period of pi, right? So it takes a distance of pi to get through the tan of x. Just bring this whole thing in. So here I'll just write the period. Actually, let's make proper notes here. Cos of x starts at, I'll say kind of starts at 0, 1, while sine of x, it doesn't really start, it goes on forever and ever, but in terms of the y-axis, while sine of x starts at 0, 0, right, kind of coming down in alphabetical order. Both sine of x and cos of x have a period of 2 pi. Right. It takes a distance of 2 pi to go through a full cycle. It takes a distance of 2 pi to go through a full cycle. Oops. Okay. Tan x is, let me see here, sine x over cos x. Hope I didn't screw that up. Who knows? I'm pretty sure. Y over x. Oh. And has a period of pi, right, as opposed to 2 pi. Okay. this usually brings up the question of, should I be in degree mode or in radian mode, right? Whenever you're dealing with trig, you've got two options. You can be in degree mode or you can be in radian mode in your calculator. And in calculus, from here on out, you're going to be in radian mode unless it's clearly indicated. Okay, so I'll make a note here. Note, in calculus, we will always use radians. Always use radians. Except when otherwise, and it'll be kind of clearly indicated. All right, so if you're supposed to be in degree mode, I'll make sure that you know. That looks weird. Okay. So like I said, I'm gonna ride you guys pretty hard today. We'll go till the very end. I'm sorry. But then we can kind of have this catalog of essential functions under our belt and we can move on and do more fun things. So the last few kind of go hand in hand, essential functions or exponential functions, exponential functions and logarithmic functions. Logarithmic functions are just the inverse of exponential functions, right? And so I'll bring in the exponential functions first. We can talk about those. So exponential functions can kind of take on two shapes, and it depends on what the base looks like, right? So if the base is greater than 1, then you've got exponential growth. Oops. So in f of x equals b to the power of x. So notice that before when we were talking about power functions, the x was the base, and then we were varying the power, right? Here, exponential functions, the x is actually in the power, and we've got some base that we're dealing with, right? And so in f of x equals b of x, we will see exponential growth if b is larger than 1. And what we'll find is it can't be 1 because then it's just a constant. And exponential decay, and maybe I'll capitalize that just to emphasize, if b is less than 1. Oops. So this is referring to the base, right? So here we have growth, and here we have decay, right? And notice that here the base is 2, that's greater than 1, so then we have this growth. And here the base is 0.5, that's less than 1, so we've got this decay. So it depends on what the base is, but if the power is x or some version of x, then you're going to have exponential growth or decay. Okay. Then finally, the logarithmic functions here look like this, and the logarithmic functions are just the inverse functions of the exponential functions, right? So they're definitely related, right? And so what's going on here is, okay, if you have, this type of behavior, right, this exponential growth, if you kind of invert it, then you get this type of behavior, right? So for the graph of a log, it looks like this. And remember, right, the domain for a log, right, one of those rules that we highlighted, we started with, was that we can't take the log of a negative and we can't take the log of 0, which is included here in the domain. So it goes from 0, not including 0, up to positive infinity, right? And so here, recall that we can't take the log of 0 nor a negative number. All right, and so that's what we're seeing here. Okay, that's it for me. You guys have been great. I haven't seen anything in the chat. Hopefully it's all okay. It's all a review, but it's just nice to have it all in one place. Any questions before we go? So I'll bump the assignment 1.3 due date till next or the following week, but make sure you get the getting started in Webassign 1.1 and 1.2, and at least get started. Anyways,
All right.
hope you have a good weekend.
You too. I'll see you Wednesday.
Yeah, crazy. Not until Wednesday. Weird. Anyways.
I'm not complaining.
Yeah.